It's great to be here today, and looking forward to talk to you in the next 40 minutes about Flink jobs as agents, stream processing for agentic AI. I think it's a very exciting topic. Would like to start with giving you a quick overview of what we mean with streaming AI agents and how specifically you can use Flink jobs to run them. Then I'd like to give you a quick overview of one specific use case, which is pattern recognition with Flink complex event processing. We'll do a few Flink SQL statement generation examples together and then try to deploy them as AI agents. And then in the end, finishing with agent orchestration in multi-agent systems and some Q&A. AI agents, from our perspective, really need access to streaming and batch data at inference to lead to a good result, to basically get full context of the environment, all the data that you have in order to trigger actions at inference, ideally at low latency. So what are AI agents in the first place? We got some definitions from OpenAI and Anthropic recently, differentiating really between agents and workflows. So in that regard, agents are more independent systems that kind of manage workflow execution, making decisions, systems that act autonomously and proactively to perform tasks, while workflows in that sense are more, let's say, deterministic, predefined code path that are executed towards a specific goal, whereas agents in that regard, as you can see, have a bit more freedom. Yeah? So in that sense, even though there are slight differences in these definitions, I think the direction becomes clear by looking at this, even though the spectrum out in production is obviously really wide between, let's say, use cases where you just will tell an agent to build a very complex software system like a mobile app. That obviously is an agentic experiences. And you might have smaller use cases that are more specifically focused on accomplishing individual tasks and goals that might more have the characteristics of a workflow, but will still be able to provide value for an organization. There also have been recent trends in order to standardize these experiences around protocols. Let's say you surely have heard of MCP being announced by Anthropic in November 2024. An approach to giving AI agents a consistent way to connect with tools, services, and data. And more specifically, kind of this allows them to have an understanding of process functions, how basically they can call individual things like APIs, and a way, let's say, if you look at the architecture of this, you have maybe a local client, or you have an agent as a client, and you have an MCP server that this agent can talk to, where you have credentials being stored on the level of the MCP server. So it enables that AI agent to talk to something like Slack or any other API that you can think of and provide a standardized interface for this agent to explore, discover, and then use the relevant APIs as tools. A new approach in that regard is agent-to-agent, being announced by Google in April 2025 as an open standard to actually enable the collaboration between agents. So if you are, let's say, imagine you're one agent and you have the context that there is another agent running somewhere else having some specific tools, you can actually enable streaming communication between those two agents via the agent-to-agent protocol. In that regard, these two protocol approaches are ways trying to standardize agent-to-agent communication and tool discovery and data discovery. So they're quite complementary in that essence. And what I'd like to add to the mix today is another approach, which is kind of building agents on event-driven architecture, which, let's say, compared to the agent-to-agent protocol, you need to know where another agent is. So you basically specifically ping another agent. Whereas in an event-driven architecture, it's nothing really new. These systems have been around for years. You basically see an agent more as a consumer of events, and then enabling the agent to react to that. And we believe that there is a strong case actually for data streaming and event-driven architecture for AI agents. So think of all the event streams that you have anyways in your organization, but also think of, let's say, data lakes. Yeah, everything that is stored for your organization, for all the historic data, and this is all context. Yeah, that needs to be pre-computed and provided to the agents for additional context to then invoke a foundation model, and from there trigger some actions influencing the environment. And what is really interesting about this, for the very first time, you actually have a feedback loop. So you actually have, again, events being produced by the agent manipulating the environment. So you not only have a full log of all the decisions a specific agent made, but you also have like a full log of the results this created in the environment that you can observe. And for the very first time, you can actually create something like accountability for decisions being made that is not possible today in a mostly human-driven decision-making world. And yeah, in that sense, we really believe that to make good decisions, AI agents require optimal context and inference. So the task is really, how do we provide that context? And this is what I try to explain to you in the next 40 minutes. We believe AI agents are at the center of the future data streaming for AI stack. So you can think of agents being able to tap into operational estate. So think of all the real-time event streams maybe coming out of your operational databases or click streams from users using your apps. And at the same time, you have the analytical estate, like all the data lakes you might have, data warehouses, all the historic data. And at the moment, it's basically, these are two worlds that are not really well connected. And we believe stream processing specifically is a very powerful tool to connect both of these worlds. In AI agents, being able to tap into both of these estates, being able to use foundation models out of the box by one of the relevant providers, but also custom AI models that have been trained on your historic data. And in that regard, agents play a very important role. We think that specifically Flink in that context can be a very powerful tool for agents. And I'm not sure to what extent you're familiar with Flink, but Flink actually comes out of Berlin, like Berlin Buzzwords, as a conference. So Flink originated in Berlin and Potsdam as a joint DFG project by TU Berlin, and then later joined by Humboldt University and Hasso-Plattner Institute. So it is an open source project, as you can see here, like widely adopted by a strong open source community, and also widely adopted in production at very relevant enterprises, mostly in the US at the moment. Obviously, the largest companies like Airbnb, Netflix, Apple, etc., Uber are real big Flink users. But also in specifically China, a lot of the large Chinese internet companies are using Flink heavily for different use cases like logistics, banking, etc. So it's a technology that's widely adopted for that purpose, specifically around combining real-time and batch data, which I think it is really good for, compared to, let's say, Spark, which originated from Berkeley, around the same time, actually, when Flink came around, but is more focused on, let's say, batch processes, processing larger amounts of data that sit in the data lake. So that might be the stronghold of Spark, whereas Flink, I think, was always more catered towards real-time use cases, and also powering batch at the same time. So now let's look at how specifically Flink jobs can be seen as AI agents, to look at events and continuously processing these events. So starting from a very basic definition of an AI agent that you can see as a microservice with access to an LLM. You can think of a Flink job being able to read from an input topic, invoke a foundation model, and write to an output topic. In that sense, I would say this fulfills this really basic requirement to see this as an agentic experience, specifically since inside the Flink job you can run stateful computation over unbounded data. In that sense, it's a really powerful pattern, even though very basic, so it might not be able to fulfill all the agentic experiences you have, but it is capable of reading from an event stream and then writing to an output topic, and from there you can actually do another thing. You can take action. Yeah, so you can, for example, connect to that output topic in Kafka. You can connect a sync connector. You can basically call on REST API this way. You can have a consumer microservice. Yeah, a very established pattern. Also something that we use quite heavily for specialized consumer microservices. You can think of, let's say, you have a consumer microservice that just reads from its output topic and then does only one thing, like sending out emails, for example. Yeah, so it's connected to an API that is in the end, just sending an email notification, for example, for data that is in this output topic. You can have another Flink job that is consuming from this output topic and then triggering action. Or you have maybe more complex use cases where you have workflows, processes that run with a lot of dependencies between each other. You might use something like durable execution engines, like restate or temporal for specifically this use case when you have a more complex workflow execution. From our perspective, the interesting thing here is that the Flink job itself can be AI generated and deployed via, for example, the Flink SQL gateway. So you have kind of both dimensions here. You have the Flink job that itself can incorporate the invocation of a foundation model, and it's at the same time you can basically use AI to generate that Flink job in the first place. This is at the moment being implemented in open source Flink within Flip 437. That work has actually just been completed last week. So there is a high chance that Flip 437 will actually make it into the next major release, which will be, I think, Flink 2.1 in the next few months. And what we're currently doing is we're trying to build an additional layer in terms of accessibility, both for humans and AI agents, to write, let's say, Flink SQL in a even more easier and recomposable way for task-specific AI functions. So you can think of, let's say, at the moment, it's still a bit complicated within Flip 437 to start invocating these models, but you can actually think of standardizing Flink SQL AI functions, like, for example, AI summarize or AI translate, and then you can use them as a scalar function directly within the Flink SQL statements you write. So this is an extension that we currently prepare, and we will start to post a new Flip over the next few days, actually, to specifically enable AI agents, to give them an additional way of tooling to work with within Flink jobs for AI use cases. There is another interesting extension to Flink, which is Flink CEP, which is a library that is actually packaged with open source Flink. If you install Flink from the Apache project, you basically will get Flink CEP as a dependency or a library coming directly with Flink, the Flink distribution. And what it gives to you is basically a standardized way of doing complex event processing, which is very difficult to do often in other languages and frameworks. And what makes this unique is really the ability to, with very few lines of code or with very few lines of SQL, you're able to take input from several input streams. You can detect event patterns, which is a sequence of specific events that need to be defined in a certain time window, for example, which is also very important to keep the memory footprint of this in line. So you never should use it without a time window. You can incorporate specific business rules, and then you can write the output into an output topic. And what really is unique here from our perspective is that we can actually then use the AI agent that created this to also react to that output stream. And at the same time, the agent is capable of creating these patterns, because there is it's specifically difficult in Flink SQL to create working patterns because the language and the syntax of the language is quite fragile around the subject. So we often see that if humans generate this code without using additional strategies like blueprints, that a lot of these jobs fail. So we can actually use AI to increase the productivity of the people writing these jobs, and we can, from our perspective, even bring it to the point that we democratize access to these tools. So we can actually bring the technology to a level that business users can start using specifically these tools to generate, for example, event pattern sequences that then the Flink jobs basically can pick up and start observing the real-time event streams that you have as an organization. And this really democratizes access to these tools because you kind of remove the requirement to always have a data engineer in between of the business users describing the problem to the data engineer implementing the pipeline, but you can kind of give them direct access to these very powerful tools. Here is an example for a Flink SQL function, match recognize, being very powerful for the use case of pattern recognition. So let's just look as a brief example how this function is created. So you actually have here a function that reads from an event stream. In this case, it's a stock ticker, and then you do some partitioning. So you partition basically by the column. In this case, symbol. So you order by the row time. You define the measures. So measures in this case are the output that the function will generate to the output topic. You define the output mode, which in this case would be one row per match. Yeah, so it will write one row to the output Kafka topic for each event pattern that it recognizes within this function. You can define the after match strategy, which means do you want to continuously analyze these, or you basically want to jump to the last row and then continue from there. And then you define, and this is specifically crucial, the pattern. Syntax, including a time constraint. What I said before is true. You should never have these functions without a time constraint because the state could grow really, really huge. So it makes a lot of sense like to limit the time constraint, for example, to an interval of 1 hour or 10 minutes, or could be 30 days, depending on the use case. But if that would be infinite, you can imagine that the memory footprint of this could be really, really very large. In that regard, we can also use or utilize AI for this manner to keep that at a reasonable amount and remind the user that they should, for example, never forget the 1 hour interval here. Then you define the pattern, the individual conditions. For example, in this case, you have ABC print with A, then multiple B events, and then one C event being defined as B price, in this example being higher than A minus 10, and C as basically then having a jump in the other direction. So you monitor kind of, in this case, movements of stock prices, and you trigger this function when you have like an unusual or very high deviation in the individual patterns of this event. Now let's put this to a concrete use case. Yeah, so imagine you're an organization that wants to do fraud detection. Yeah, so we generated here like a little example. So we used for that purpose a tool called Shadow Traffic that creates synthetic data into, let's say, an output could be Kafka, but you can also produce the data towards a Postgres. In this case, we create users, we create user logins, we create transactions with synthetic data. And we kind of tell it to put in some fraud. So we basically define fraud according to some typical fraud patterns. And then we monitor the transactions for, let's say, in this case, the amount of fraud that we will have within these streams. So the good thing about Shadow Traffic is you can actually tell it to put a certain amount of fraudulent transactions in, like, for example, 1%, and then you can observe in the end if you basically detect 1% of fraud within your output topics. What we do here is basically we then use the agent to get in that context, create the patterns, write the output, and then trigger actions from that angle. Two very concrete examples here. So one often used pattern for fraud detection is you monitor within a 1 hour window several small transactions, in this case being defined by amounts smaller than $100, followed by a very large transaction. So this would be one pattern. Doesn't mean that all of these patterns are fraud. It just means that these are fraud candidates. So what this function here does, and this is kind of AI generated with a blueprint that we used with any random foundation model. I will talk in a minute about how we actually benchmark those. But this would basically give you then this function, and then you can deploy this function as a Flink job with, let's say, the Apache Flink SQL gateway, or you can also just use the SQL CLI within Apache Flink. So you basically just need open source Flink and in this case Kafka being set up and being integrated to start using these patterns and using this as a way to enable AI agents to do pattern recognition. Another example would be rapid fire transaction patterns. So you have 5 or more transactions in a 10-minute window, smaller than $10. Obviously, these would have to be adjusted. And it's very important also in that sense. So this statement will fail. Let's say if the model will hallucinate, for example, a row a column that is not there. Yeah. So in this case, let's say if you are reading the partition by user ID and there is no user ID in your topic, obviously this function will fail. So in that regard, it really is important that you also give the AI model the right context about your data infrastructure, which, so for example, also how this underlying Flink table looks like or the relevant corresponding Kafka Kafka topic. For example, in this case, also to get the timestamp column right, yeah, so that the function is able to order these events in the right order. So you need to specify, obviously, that this is the relevant column. And then also for the output topic, you should also be able to get some consistency in there so that in case you change these functions, that it always will adopt to the data model of the relevant output topic. In this case, it puts out transaction time, last transaction time, and the transaction count, the transaction sum as relevant columns for the output topic. So in that regard, it's very important to also to look out for consistency. In this case, as you can see here, you define the pattern within a 10-minute interval, and you define A as A amount smaller than 10, and you deploy that job. Ideally, you can then monitor in the output topic that data is being produced. Another example would be, now we go to the user logins topic that we just created via shadow traffic, and we monitor here from logins from different IP addresses and countries in a 30-minute time window. So this would basically result in a function like this, where you match recognize partition by user ID, order by timestamp. You define the measures of the output topic. You basically give the pattern and the conditions, in this case being defined as A as A IP address is not null, and A country is not null, and B as B country different from A country, and B IP address different than A IP address. In this case, you have a very simple pattern again that will give you as an output these login anomalies being written to the output topic. Obviously, this doesn't mean that all of these logins are fraudulent logins, but you can actually flag them as such, and then you can define, dependent on the output, you can add additional measures. Like, for example, a more advanced way here would be to add statistical models, where you can, for example, calculate the distance between the countries where, for example, this fraudulent login might have happened. So you basically can observe, okay, maybe it's realistic to travel from Luxembourg to Germany within 30 minutes, but it's not realistic to go from South America to Germany. Yeah. So this obviously can be done much more advanced here, but it already gives you quite an interesting, let's say, level of accuracy and level of value for very few, a very low investment actually. So what we do with Airy is basically we add a level of standardization on top of this. So we kind of offer an AI agent suite to build, connect, and govern continuous stream processing agents. I mentioned this specifically because there is one component that powers a lot of these experiences on top, which is something we call schema intelligence. And this is really crucial. So I wanted to quickly show you how the architecture of the system is being built. So we have an open source conversational platform that we developed a couple of years ago. In this case, it's powering REST APIs and WebSockets. It's Apache 2.0. It leverages Apache Kafka underneath, which is also open source, leverages vector databases and Postgres, also Neo4j recently. Also open source infrastructure, data lakes, very important subject, obviously, Iceberg, Delta, etc., being open source standardized table formats. And then Flink as an open source component, in this case invoked via the SQL gateway, and then can be connected to, let's say, external models directly via Flink. We have this additional AI agent suite. Yeah? It's obviously also something that you can build yourself. We built that kind of as a predefined component, which is not open source yet. So we're currently thinking about how to make that accessible in the best possible way. We're working at the moment with several selected partners to develop this application, but I can also already show you the principles behind it, which is in this case a backend and a frontend, obviously, so it has several UIs, leveraging an LLM connector that can invoke locally running models via VLLM. Yeah, would be fully open source, so you can deploy a local llama to this. Might be very crucial if you're a bank or an insurance company that needs to run everything on-prem, or if, let's say, your use case is a bit more relaxed in terms of requirements, data privacy, and other factors. You can also obviously use any kind of AI model. And then it leverages something like Flink connector, which is, let's say, a standardized way of calling invoking Flink and calling the Flink SQL gateway. Of course, this is something we built here, also leveraging Kafka. It depends a bit on how many requests you have. So if you just use it kind of to explore this technology to build very simple agents, it might not be worth standardizing it. If you are very large organizations running, let's say, for example, somebody like Netflix, they run 20,000 Flink jobs a year, and they're growing 30% or more. Then you might want to standardize this because you have a much larger amount of Flink jobs being created and having to be continuously monitored for successful completion. And in this way, I think this makes a lot of sense the more Flink jobs you're running as an organization. So what is schema intelligence? It's actually a layer that provides semantic understanding for our agents with metadata. So in that case, we actually import the data from data catalogs and schema registries, and we annotate that data. So we actually use AI models to generate examples how that data is actually used. So what the data means, yeah, and how the data is used. Because often when we look at schemas out in the wild, we often see that people don't really have well-documented schemas. So often, like, the comment fields are empty, or it's not really useful, what we find there. So in this case, the approach is to use AI-generated comments, not only looking at the columns and the types of these relevant fields, but also looking at example data. So it can read, for example, the last 50 or 100 events, in case you have a privacy-sensitive use case, and you might not want to do that. So it can even, let's say, for cryptic column names, yeah, like CC, it could actually see it's a credit card in there, or it's a social security number, yeah. So we can actually flag the relevant column as PII information, and even mask that, and basically say you don't want to expose that information downstream, but you want to basically keep it restricted and don't use that specific topic, for example, for a specific AI agent use case, because you don't want to expose this information, this critical privacy-related information, to the AI agent. So this would be one example use case for schema intelligence. Something we also do in that regard is we try to read and understand business process documentation, which is really interesting because that goes very well together, because you provide context to the agent of what is the happy path. How does the process look like? What are next steps in the process? So you give it additional context, not only how the data is used, but also how that data is used in a business process context. And this way you can actually do something like process mining in real time, yeah, where you are able to detect if SLAs are not met, or if, for example, a process deteriorates or takes too long, or actually there are some steps in there that shouldn't be there, also by enabling AI agents to try to bring it back on track. We do then the indexing in vector databases and knowledge graphs. We also use Postgres as a metadata store in between to provide a low latency index that, again, the agents can use to get an understanding of where the data is, and to be able to use that data on the fly in this context to provide successful output at the lowest possible latency. How the data is used then on the querying and Flink SQL generation side is we have a search service that talks to a foundation model, in this case to generate the embeddings. We look into the vector index, we look into the relational knowledge graph. We give back via the search service the relevant hits to the, in this case, SQL editor that will start building the SQL statement. Obviously, it's connected to a foundation model, and we have our blueprints and additional documentation stored in a Postgres database. So for example, let's say if you look at the pattern recognition example I showed before, that just adds around 8,300 additional tokens, which is quite cheap for most of the foundation models, but it gives you a higher level of accuracy in the Flink SQL statement you generate. So we make that accessible to the foundation model when we task it to generate a specific Flink SQL statement. And then together with the blueprints, so these are successful ways of completing these queries for different, let's say, sometimes complicated statements like joins, window functions. We get to a higher level of accuracy in building these statements. Then we open a WebSocket connection to the backend, deploying that job. We track the job also via the Postgres database as a metadata store. And we then observe if the Flink topic is, the Flink job is being deployed successfully, producing data to the relevant output topic, or if it's maybe failing. We can actually then give that back to the Flink SQL editor, enabling the user to react to that and maybe debug the query. The level of accuracy that you will get without the system, like schema intelligence, is roughly 30–40%. So that means, in terms of successful completion, that 30–40% of these queries will will eventually be completed successfully, whereas everything else fails. So this is without schema intelligence, just the table names and columns. And you can get to 70 to 80% with schema intelligence, but without the blueprints and documentation. And what we see is that with additional curation, blueprints and documentation, and schema intelligence, you get to 90 to 95% of successful completion, which is a level that is almost at the level, I would say, where it really makes you much more productive as a data engineer and data professional, and where it's almost as good that you can give it into the hands of a business user. Yeah, so to make, in this case, data in your organization more accessible to also business teams. Obviously, that requires some curation because they might use specific language that you then need to kind of give to the workspace. You might want to limit the amount of access that the relevant business team has to a certain amount of topics. You don't want to give the marketing team access to the entire data the company has, but you want to curate this workspace in a way that you enable the marketing team, or you enable a research analyst team or a risk team at a bank or insurance company to use these new tools in a useful way. There are some industry benchmarks that have been created around the subject, which kind of make our case here that you have similar levels of accuracy in the industry. So this is a bit of an unfair comparison because here the results of that benchmark kind of that you can see here in the 20 to 35% accuracy bucket, they are pre-annotation and pre-discovery, basically. It's just the table names and columns. Whereas, let's say in this case, the examples for the 70 to 90% accuracy, they are with some pre-processing where there's some additional discovery happening. So it's not a totally fair comparison, but I think you will see that this goes a bit in the right direction that we also talked about before. So how this works in the product is, just to give you a quick example here, is you see here it's empty. We now generate the description AI generated for the relevant table and for each column in a let's say Postgres or Flink table, and the same would work also for a Kafka topic. So we could take, let's say in this case, any kind of schema. Here is an Afro schema, and we then use AI to annotate that schema using specifically the doc field that is added to each subject. And then we use this again at inference to point the AI agent in the right direction of where the relevant data is a user might look for, and how the data is used. Another application for it would be a SQL editor, where you have an AI assistant kind of being context aware. So the AI assistant here sees what the user is typing in terms of the queries the user writes, and can help him to autocomplete and correct these statements at the same time. It's a bit like Cursor. If you think of coding, you can actually give it instructions in natural language, like what is the data you're looking for. In this case, for example, top 5 customers, it will autocomplete the relevant topics, so it has knowledge about what is your underlying data infrastructure, and then it starts to generate these statements. You can kind of directly copy them over, so with this little use code icon here, and then you can run the statement, and then you have a way also to automatically fix it, ask additional questions, run the variant statement. It will basically try to help you complete this data discovery problem. The additional UI we just mentioned before is a business user focused UI, where you have data that the user might ask for that is nowhere materialized as such, but we basically use these capabilities. We use the Flink job to join the data in real time. So this query here would update continuously. So you can also do things like, let's say, the business user might ask to continue update this query for the next 2 days. You can actually create a long-running Flink job out of this and combine it with a trigger, in this case, sending hourly updates or sending you updates when a certain number is outside of a specific range. So you can use pattern recognition also for these kind of tools, enabling, again, like business users to work more closely with the data, democratizing access to the data, really fulfilling the premise of data mesh, to have reusable, on-demand generated data products that are also accessible to business users in an organization. We then have a collection of pre-built streaming AI agents for complex event processing. So think of these are experiences where basically users can just pick from a catalog of apps or agents in this case and just deploy them with very few clicks. So think of a fraud detection agent And in this case, it's a low-code, no-code experience where we would enable a business user to write an unusual transaction pattern detection mechanism within a fraud detection agent, just with basically using a conversational tool like this. So could be a form, but in this case, it's basically a very simple pattern of writing this match recognize function and then triggering an action in response to that, also giving it access to an AI model that can be used. And of course, the same thing would apply to, let's say, if you were not to use it with one of the predefined agents, you could also use it by just by creating the agent on the fly, going through a sequence of questions. So in this case, you would, for example, say, give me an agent that detects fraudulent activity by checking the user logins and detecting unusual IPs. Here, you would, like the system would suggest a name, and it would also start looking for where in the data infrastructure do we have data that fits to this problem. Yeah, it selects a certain selection of data sources. Yeah, in this case, for example, user login table and transaction tables. And then also tells the user why it thinks that's the right place to look for that data. And then it kind of tries to enable the user here to build this agent, also suggests some patterns to look for. So these patterns can be adjusted. Yeah, so you can basically write your own patterns this way. And then we use AI to translate those pattern descriptions into standardized and correct Flink SQL statements, and then deploy them. So I think you can think of like the next steps. They're in line with what we showed before. But I think overall, the use case is here to make a very powerful technology like Flink more accessible to users across the organization. And then the statement is being generated and deployed and runs ideally to successful completion. So what are concrete use cases that you could apply this for? So think of a multi-agent AI system to resolve supply chain disruptions. You could think of real-time weather data, inventory data, and then you might have a model like a delay model that is being used by an inventory agent that detects patterns for supply chain disruptions, write them into an output topic. You have an escalation agent reading from that topic, providing, suggesting relevant solutions. They go into another topic. And then one very important thing is, at the moment, we don't really see agents being used and, let's say, reroute shipments independently from human involvement, but we really see the need for user interactions. And this is where our conversational platform comes in, so we can actually observe what the users are talking about in Slack, and we can also use that channel, like Slack, MS Teams, emails, other communication channels, as a way to include users in these agentic experiences. So in this case, the agent could send a suggestion for a rerouting of a shipment to a human user that is in charge and competent of making that decision. So you have the agent do that suggestion, and then you might get the approval or not, and then you reroute that approval back and and resolve the approval and reroute the relevant shipment or not. Yeah. So in this case, you make what the agent suggests also accountable by adding this level of user interaction. Another example would be, for example, predictive maintenance, really a super important use case for the aviation industry or also for oil and gas. So you could think of some sensors that continuously produce data. You have a failure monitoring agent that selects failure candidates. You have a repair model that basically predicts when a specific component should be repaired. You have that as a suggestion. You then again get human approval, and then you have a maintenance action agent in the end to resolve that approvals and task the relevant repair tasks to be executed, ideally before the plane is flying somewhere in the world and it's very expensive to ship the relevant part to that other part of the world. Last use case I wanted to show today is an AI use case, where in this case you could have, let's say, a self-supervised event log analysis and monitoring. So think of logs and event streams. You have a log analysis agent that basically uses a collection of event patterns to detect anomalies, and an escalation agent to score those and basically put them as potential incidents before they actually happen into an output topic of system incidents. And the interesting thing here is you can actually automate the pattern generation by actually having an agent that continuously produces candidates, via invoking a reasoning model here to produce new, maybe implausible patterns, and then you could have a test agent testing these patterns against the historic data you have as an organization. And this is a very interesting pattern that we see because the foundation models are quite good to come up with new and interesting patterns. Not all of them make sense. Sometimes the pattern is really off, but it's a very interesting use case from our perspective to really use the capabilities of reasoning models in a let's say more creative way that you can then basically benchmark with the existing historic data that you have, and then rate and score the relevant patterns and deploy them, maybe make them part of the collection of patterns you want to continuously monitor for. So this is the end of the presentation. If you have any AI agent use cases that you want us to look into, that would be lovely. If you could kind of let us know about it, we would be very happy to learn from you and from the use cases you think this could be useful for. We're still in the early days of AI adoption and specifically stream processing for AI and AI using stream processing. So in that regard, happy to take any questions. Also, feel free to add me on LinkedIn or shoot me an email whenever you want to continue the conversation. So thank you for listening and coming to my talk, and happy to take any more questions.
Thanks for the talk, Steffen Hoellinger. Do we have any questions? Also, no online questions right now. I think everybody is overwhelmed.
There's one question here.
Okay, there we have.
It's also the end of the conference. Everybody's tired.
Yeah, so it's a question about the confidence of the predictions and recommendations that you're making.
Yeah.
Regarding the business process analysis part.
Yeah.
Because I work at SAP Signavio, so you know the process mining, and we did something like this with Gemini 2.5, so one of the newest things with agents, and we went in depth. And yeah, the model was giving different recommendations every single time, even though the input was the same.
Yeah.
One time it was saying we should do that. The other time it was saying we shouldn't.
Yeah.
So, yeah, what's your confidence about that? Like,
it's an extremely good question. I think it depends on how well you annotate the metadata layer for it. Yeah, because specifically for that use case, I've been also looking into that quite intensely recently. Specifically, the process mining use case. I think the level of annotation that you normally have, specifically if you're working with batch exports, is not high enough. Yeah, so basically you can increase the level of confidence from my perspective by first running that continuously, so to give the model more context of what is actually happening and not reconstructing that in a simplified event log just after the fact has happened. So adding real time to the context will improve accuracy, and adding more metadata to the context will improve accuracy. So you can use that as an input for the relevant AI models that score or recommend these relevant outputs to guide the user in the right direction and to increase the level of confidence and consistency within those queries. So ideally, you shouldn't end up basically with ambiguous recommendations. That's obviously the goal, and I think there are ways to get that under control. Yeah, but it requires basically that we move a bit out of the batch world that we're often still in because it's easier. Yeah, it's easier to do a one-off batch export of ERP data. And instead, we basically need to come to a real-time computation of stateful events and to really give the full context to the model at inference. So the model has also a higher chance of giving an accurate and consistent recommendation. I think this would be my answer, even though it might not fully satisfy you, but I think it will not come for free. So there is a lot of effort that you need to make in order to upgrade systems, in order to basically make these systems consistently work with the data in real time, incorporating the models in the right way, and using the right amount of metadata and annotation and curation. So altogether, I think it's an advantage, but it can be worth it. Yeah, the investment.
All right, thanks a lot, Steffen Hoellinger, again. I hope you hang around to answer more questions.
Yes, any more questions, happy to answer them after the session. Thank you very much. Pleasure.